All right, guys, we're going to go ahead and take a look at polar graphs and also derivatives of polars today. Okay, and hopefully we'll do a couple examples so that you can figure out the homework tonight, and then I'll answer any questions on Monday. All right, I gave you a sheet yesterday that had all of the different types of polar curves that we usually will see. All right, we have limacins, that a plus or minus b cosine or sine of theta. Now there's different versions of those. All right, you may remember some of those from pre-calc depending on what the ratio is of a to b. All right, we have our rose curves. They're the fun ones that have the petals involved. And remember that if n is even, okay, that n value here, if it's even, there's 2 n petals. If n is odd, there is that number of petals. So if it was 3 theta, then it would be 3 petals. If it was 4 theta, then we'd have 8 petals. We have circles, which is a new one. We didn't really talk about that in pre-calc, but it's pretty much the same as rose curves, just with 1 petal. And then lemniscates, which is a special one that looks like the infinity sign. All right, you have that as a reference so you can look at it as you're trying to graph these. All right, the way that we graph them in calculus is actually based on their trig graph themselves. So if I rewrite this as r equals 3 sine of theta plus 3, we got to think of what's happening to the trig graph here. Let's think of this as a regular trig function. All right, there's a 3 in front of the sign and plus 3 here. Well, the 3 in front of the sign would change my amplitude. My amplitude would be up 3 and down 3. The plus 3 is going to shift my graph up 3 units. So if I were to do a little sketch of this, without the 3, we know that sine has a period of 2 pi. Here's pi, pi over 2, and 3 pi over 2. Normally sine is at 0, and then if the amplitude is 3, it goes up to 3, down to 0, negative 3 here. But we're shifting it up 3 units, so now each of these points are going to go up 3. So here it's going to be 3, here at 6, at 3, here at 0, and 3. All right, well now let's apply these points to what we looked at yesterday with plotting points on a polar coordinate system. All right. All right, well what's the highest value we're going to have here? And if you look, the highest value is 6. So we're going to make 6 concentric circles. So 1, 2, 3, 4, 5, missed. Maybe one more. 6. Okay, so here's my polar coordinate system out to 6. Let's go through the points. At 0, 3, I have a point. We got to remember, the degree is 0. So 0 would be our polar axis. So 0, 3, 1, 2, 3. I'm going to put a dot right here. All right, let's go around. Keep going. Next is pi over 2, 6. Well, pi over 2 would be straight up, so that would be 6 units away. Now pi, I'm at 3 again. So here's pi, 3 units away, 1, 2, 3. Okay? At 3 pi over 2, I'm at 0. And then 2 pi, I'm back to 3. Well, let's see what this graph is as well. Here, if I look at this, this is a limacin graph. Okay? And the limacin graph, if we look at our ratios on our piece of paper, when a over b is 1, it's a cardioid. So what I have is a graph that's going to start here, work its way up to here, back down to here, and underneath, it's going to come back up, go back to 0, back to here. All right, and we can kind of gauge where those values are based on our graph of our trig function. Okay, so by plotting out the points, we can see exactly how far apart those are, and we can do more points if we need to. Let's say we need to figure out what pi over 6 is, or 11 pi over 6. We can plug that in and figure out roughly where would that be at, and we can plot those points. Let's go ahead and do another one. Let's do r equals 5 sine of theta. Okay? So 5 sine of theta, we can see is going to be one of our circles. Well, let's graph that and see what it looks like regularly. We know that that's going to have an amplitude of 5. So with an amplitude of 5, here's 2 pi, pi over 2, 3 pi over 2. It means it's going to go up to 5 and down to negative 5. Starting at 0, we're going to go up to 5, to 0, negative 5, and here. Yes, that's okay. All right, so here's my trig graph. Now from here, I can see my highest value is 5. So let's go back to our polar coordinate system, and we're going to do 5 concentric circles. And really what I should be saying is the highest value is 5, but it's really the furthest value from the x-axis. So it could be negative as well. It could be negative or positive. So 5 on either end, it still is the farthest away. So let's go 1, 2, 3, 4, 5. Okay. All right, so here at 0, all right, we're at 0. So let's go ahead and put a dot at 0, 0. At pi over 2, we're 5 units away. So pi over 2, 5 units away. At pi, I'm back at 0. Okay. 3 pi over 2, negative 5. Well, remember with polar coordinates, when you get a negative, all right, it wouldn't be just 5 here, it would flip it back to 5 up here. So what we end up getting with this is it's just going to keep going around in a circle like that. Or one petal if you want to think about it. Okay, we just keep going back because you see how 2 pi is back to 0 again. All right, so again, knowing what the shapes look like before you get started will help you in figuring out the graph. Let's do another one. Let's do r equals 1 minus 2 cosine of theta. All right, so 1 minus 2 cosine of theta. Let's rewrite this as r equals negative 2 cosine of theta plus 1. So now we can see we have an amplitude of 2, a vertical shift of 1, and that negative is going to flip our graph. Well, let's look at our cosine graph here. 2 pi, pi over 2, and 3 pi over 2. You can see why you really need to know the graphs of those trig functions. All right, so normally, let's do just a parent function with the 2. With an amplitude of 2, meaning it's going to start with 2, it's flipped, so it's going to go down to negative 2. Pi over 2 would be 0, pi would be positive 2, 0, negative 2. So this is without the vertical shift, like that. Now let's go ahead and add that shift up 1. So now everything is going to go up 1. So here, this would go up to a 3, negative 1. This would be at a 1. All right, so furthest spot from our x-axis is 3. So let's do 3 concentric circles. 1, 2, 3. Okay. Now if we look at this, this is another Lumeson graph. So let's see what we have with this. All right, starting off with 0. Well, 0 is at -1. So at 0, all right, which is this line here, instead of 1 value, it's going to be over here for -1, because remember, we flip it back. Okay? At pi over 2, it's +1. So here's pi over 2, here's +1. Okay? At pi, we're at 3. So here's pi, and here's 3 units there. 3 pi over 2, we're back at 1. So 3 pi over 2, 1. And then 2 pi, which is here, we're back at that -1, which flips over. Remember, if we look at our ratio here, 1 over 2, this is going to be a limacin with an inner loop. So if we start here at this value at 0, -1, what's going to actually happen is we graph these, we see that, okay, what's going to happen here is it's going to get closer to the x-axis. These values, they are all negative, and so they're all going to flip back to over here. So here we have this graph going in this direction. All right. Here they're positive, they're going to come back to the 1. And then we're going to keep going until we get to the 3. And then back till we get to 3 pi over 2. And then work our way back around till we get something like that. There is our limacin with an inner loop. All right, and see how, again, these are negative and these are negative. And that's why where we're at those angle spots, it's flipping back to these points here. All right, these are all positive, so like if we were to go just before pi over 2, you see how these are in line with that in that quadrant. All right, so they get a little tougher as we go. You have to really look at those values. Let's do one more. Let's do a rose curve. R is going to equal 3 cosine of 2 theta. Now right off the bat, we should know that with that 2 in there, we're going to end up having 4 petals. But let's graph this. All right, graph's a little different because now we have a 2 in here. And remember, that changes the period of my sine and cosine. The period for sine and cosine is always 2 pi over b. So if I put a 2 in there, my new period is going to be 2 pi over 2, which is just pi. So here's my graph. Have an amplitude of 3 again. I'm going to do pi. I'm going to split it in half to pi over 2 and split those in half to pi over 4 and 3 pi over 4. All right. Now, amplitude of 3, that means cosine is going to start off at 3. All right. It's going to go down to 0, down to -3, up to 0, up to +3. Okay, if we need to review how to graph these, come see me, we'll go ahead and review it. Well, let's see, the furthest distance from our x-axis is 3, so let's do 3 concentric circles. 1, 2, 3. All right, so at 0, we're at 3. So here's our 3. At pi over 4, we're at 0. So pi over 4, we got back to here somehow. Now notice these are all positive values. So that means they're going to be in the same quadrant as the angle. Okay, pi over 4, let's do pi over 2. Pi over 2 is -3. So here's +3, but since it's negative, it's going to flip it down here. Well, these are negative, so these also would have flipped down, and it kind of goes in the same pattern like that. All right, 3 pi over 4, back to 0. Again, they're still negative, so here, they're going to come back to that point. Pi, we're at 3. So this is going to actually work its way back here. Now you know there's supposed to be 4 petals. And we only did 1 period, but if we keep going and graph another period, you can probably see what's going to happen. we're going to finish out that pedal, and then 3 pi over 2 is going to give us there, and then finish out our last pedal right there, giving us our 4 petals of that graph. So hopefully that made sense. I know it's a little tricky trying to figure out the whole positive, negative R values and kind of keep it going in the curve. But remember, if it's positive values on this graph, it's going to be in the same quadrant as your angle. If it's a negative value, then it's going to be in the opposite quadrant, okay? Just like our petals were here. The other thing we have to talk about is derivatives of polar equations. And they're a lot like derivatives of parametrics, and that's why they're grouped in the same chapter. So let's take a look at derivatives real quick. All right, just like with parametrics, when we got to take the derivative, we're going to take dy over dx. But since we're dealing with things in terms of theta, all right, we're going to go ahead and do dy over d theta over dx over d theta. Just like we did with parametrics in terms of t. And just like with parametrics as well, we can find our horizontal and vertical tangents this way. We know that the numerator, if we set that equal to 0, we can find our horizontal tangents. When we take that denominator and set it equal to 0, we can find our vertical tangents. All right? Now the trick here is realizing, okay, how do I find dy over d theta or dx over d theta? Well, let's start off with an equation like r equals 2 times 1 minus cosine of theta. Okay? Let's start off with finding the derivative. Find dy over dx. Okay? Remember, we learned today about how to convert from polar to rectangular. And we learned that x equals r cosine of theta, and y equals r sine of theta. Well, the equation that they've given you in polar is r. So we're going to take that r value and we're going to put it into these two right there. So this whole thing right here is going into this r and this r. So x is going to equal 2 times 1 minus cosine of theta times cosine of theta, and y is going to equal 2 times 1 minus cosine of theta sine of theta. So now we have our x and y equation in terms of theta, and now we can go ahead and find the derivative of each of those, which is a little lengthy. All right, but I trust you guys can do it. So let's go ahead and I'm going to distribute. Why not? Make life a little easier for us. So I get 2 cosine of theta minus 2 cosine squared of theta. And here I'm going to distribute and I get y equals 2 sine of theta minus 2 sine of theta cosine of theta. Which if you really want to get fancy, you could go ahead and do sine 2x. Let's take the derivative. In terms of theta, dx over d theta is going to be negative 2 sine of theta. Here we're going to do chain rule, so negative 4 cosine of theta times negative sine of theta right there. Okay? And then we're going to go and do the same thing right here. dy over d theta. We get 2 cosine of theta. And here we got to do a product rule, unless we did change it to sine 2x, which would make life a little easier. But let's do a product rule. All right, so first, d second, which is going to be sine again, so put a negative, so I'll change that to a positive, sine squared. And then minus second, d first, which is just going to be 2 cosine squared theta. Okay? So we get all of that. So now let's go ahead and dy over dx again, dy over d theta, or dx over d theta. So I'm going to take those two values, all right, and I'm going to put them on top of each other. So our dy over dx is going to equal 2 cosine of theta plus 2 sine squared theta minus 2 cosine squared theta all over negative 2 sine theta plus 4 cosine theta sine theta. Ooh. So this would end up being our derivative for this polar equation. From here we can find our horizontal tangents and our vertical tangents by setting them equal to 0. All right? Gets a little tricky, but again, here we can actually use our double angle identities to help us out with this one. And here we can just factor out sine of theta. This would be a kind of easy one. All right, well, let's check that out. Let's do it. So I'm going to erase all this. Okay. I'm going to leave that down there for a moment. We're going to find the vertical tangents. Vertical tangents are going to be setting the denominator equal to 0. If I look at this, I know I can take out a negative 2 sine theta. So negative 2 sine of theta is going to give me 1 minus 2 cosine theta. I love it when it works out that way. Negative 2 sine theta equals 0. What does theta make, or where is sine 0? Theta is going to be 0, pi, 2 pi, and so on. And here we have 1 minus cosine theta equals 0. So cosine of theta equals 1 half. Well, where's cosine 1 half? Theta would be pi over 3 and 5 pi over 3. We usually work on that interval of 0 to 2 pi. All right, so those would be where our vertical tangents are. Okay? So, all right, so let's take a look at our horizontal tangents. Now, these are ending up giving us the same point, I believe. So if we go back to our original, we really don't need the 0 and 2 pi. We can just worry about pi, pi over 3, and 5 pi over 3. Just like when we were graphing there for a moment, if it just keeps repeating the same spot, we don't have to worry about those. We only need one. Okay. All right, let's take a look at those horizontal tangents now. All right, horizontal tangents. Let's set this numerator equal to 0. Plus 2 sine squared theta minus 2 cosine squared theta. Excuse me. Set it equal to 0. All right, now if I look at this, okay, I got a couple options I can do. I can change it all into cosine, or if I switch this around and take out a negative 2, which would give me cosine squared theta minus sine squared theta. Okay, scratch that. That's not going to help in this case. All right, I take that back. Let's go ahead and change this to 1 minus cosine squared. Now I got everything in terms of cosine of theta. Let's simplify this. I get 2 cosine of theta plus 2 minus 2 cosine squared theta minus 2 cosine squared theta. Let's rewrite this so that it's a nice trinomial. So minus 4 cosine squared theta plus 2 cosine of theta plus 2 equals 0. All right, so now we have to do a little factoring. I'm going to divide everything by negative 2, make life a little easier. So it's 2 cosine squared theta minus cosine of theta minus 1. All right, so now I need to factor this. Well, it's like any other trinomial. You have 2x squared minus x minus 1. So we know we're going to have 2 cosine of theta and cosine of theta to get that. And I gotta get -1 here, so I'm gonna do -1 and +1, because I know -2 plus 1 is -1. All right, so I'm gonna get rid of this guy because this is gonna get in our way. This, we're looking for where cosine of theta equals -1/2. And this one, we're gonna look for where's cosine of theta equal to 1. And so cosine of theta is equal to 1 at 0 and 2 pi. And here, theta is going to be for -1/2, 2 pi over 3, and 4 pi over 3. All right, so everything I just said about 0 and 2 pi in the last piece, forget, because just like with parametrics, if they have the same value for horizontal and vertical tangents, that's where we need to cancel them out. That's where it's indecisive, we can't figure it out, inconclusive, I mean. So when it's inconclusive, that's where from the other ones, we can cross those out. Not that they were the same, scratch what I said about that. So because we got 0 and 2 pi for the vertical tangents and for the horizontal tangents, we don't use those, we only use the unique ones here of 2 pi over 3 and 4 pi over 3, okay? So that's how we would figure out the horizontal and vertical tangents and the derivative for polars. So hopefully with all that, you can figure out the homework for tonight, figure out the AP problems I gave you for Friday, and then we will review everything on Monday, okay? Hope you guys have a great weekend.